Good afternoon, students. This is EE330. We're continuing with chapter 1 lecture. So we reached to op-amp. Circuit. So usually as a review for the op-amp from 211. So this is the op-amp. Most likely this is V0. Those are the positive range, the negative range, and those are the input voltage. So usually if the positive voltage on the positive is non-inverting, when the positive is on the negative and the negative positive, so usually this is an inverting. So for non-inverting amplifier, so this is a high gain voltage, high gain voltage. And for the setup like this, we're talking about non-inverting. So usually the output voltage in terms of this and in terms of this voltage, so most likely V0 has to be greater than V0 low, which is this one, and less than V0 high. So this is as for the op-amp circuit. So in case if we introduce so positive here, positive, this is non-inverting, and the negative will go to the output. We have R1 here, R2 here. So this is V0, V negative. In this case, it's V1. So in order for us to get the voltage across here, we use voltage divider. So we have Vn, which is equal to V1, is equal to, this is R1, divided by R1 plus R2, multiplied with the voltage on the output. So to fix this one a little bit better, we're going to have V0, 1 plus R2 divided by R1. R1 multiplied here, and then R1 will go on top. So if the op-amp, as we learn from 211, when we were talking about ideal op-amp, that means the negative terminal voltage is equal to the positive voltage is equal to V1. or is equal to 0. So in this case, V1, because we have a 0 voltage here, which is V1. So we're going to substitute whatever voltage here for Vn, knowing that the gain is equal to V0 divided V1, which is when we set up this, we're going to end up with V0 is equal to V1, or divided by V1, 1 plus R2 divided by R1. This is for non-inverting amplifier. So it's just like to put things into perspective. Application for diodes and for transistor can be expanded significantly if we put these devices with the operational amplifier. So most likely, if we put those devices together with the op amp, so we will accomplish a high gain voltage amplifier. High gain voltage amplifier that accepts 2 inputs. So in this term, we can call those 2 inputs as Vn, which is the inverting input, and Vp is the non-inverting. Okay, for the inverting amplifier, change the page. Inverting op amp. So most likely, if we are inverting, we need to put the positive into grounding, V0. We have R1, this is I1. R2. We have V0 here. Also V0 here. And this is V1. So in this term, same thing, we're dealing with ideal op amp, which is Vn is equal to Vp is equal to 0 in this case. Before that, there's no resistor here, so there's V1 will be equal to 0. But now we have a resistor, and to find the gain, which is V output divided by V1, we need to use Ohm's law. So considering that this is our node, so V1 minus 0 divided by R1 is equal to 0 minus V0. divided by R2. And considering V0 divided by V1, which is equal to the gain, is equal to negative R2 divided by R1. There's another third kind of amplifier, is the summing amplifier. Summing amplifier is when you have an amplifier with two voltage source at the same node. So we have a resistor here and a voltage source. And also we can add so most likely this is V2, this is V1, R1, R2. Currents are flowing in the same direction. And we're still in the inverting process. This is R3. So usually this point, it's at the same point. This is the summing junction. We use node voltage to get the gain. And so we have V1 here, V2 here. This is our op amp. So most likely this is our V0, or you can consider this is 0 voltage. Let's name it, this is V0. Let's put it as a Vx. So V1 minus Vx divided by R1 plus V2 minus Vx divided by R2 is equal to Vx minus V0 divided by R3. Knowing that Vx is equal to 0, and let's say if assume R1 is equal to R2, so solving for V0, negative R3 divided by R1, V1 plus V2. This is the equation for the output voltage for the summing amplifier. Voltage buffer. What happened when the voltage is passed as a buffer? If R2 is equal to 0, that means R1 goes to infinity. That means the gain is at 1 for non-op amp. Non-inverting. And why we do this? To eliminate inner stage loading. So what happened if we introduce a diode into the op amp circuit? So now we finish a review for op amp. So diode op amp circuit. So if we have an op-amp, and let's say we have R1 here, and we're going to introduce a diode here, another diode here, R3, R1, R2, and we have V0 here. We're going to provide a voltage source, V1. Let's name the diodes D1 and D2. So R1 here. So most likely, if we are talking about a diode output voltage without the rectifier, so we have this output signal. Due to time. So when we introduce the diode to the op-amp circuit, the output voltage here will be rectified. Why? This circuit here is called half-wave rectifier. So what happened here, we need to take into consideration two cases. We have to take into two cases. Number one, when V1 is greater than 0. So since this voltage is supplying this circuit with two diodes, when V1 is greater than 0, one of these diodes will be forward biased and the other one will be reversed. And when we have V1 less than 0, one of this diode will be reverse biased. So for two cases, I put in a different color, when V1 is greater than 0 and V1 is less than 0. So we're gonna start with the first one. So what happened here? If V1 is greater than 0, so the current will never pass through here. So it will be finding its way through D2. So D2 is on. That means V1 is equal to Vp, and also V1 is equal to Vn. Why? Because it's ideal op-amp, Vp is equal to Vn is equal to 0. So in this case, D1 is off. So we have the Vn is equal to V0 and V1 is equal to Vn. That means V1 is equal to V0. Simple as that. V1 is equal to V0, 1. So that means all of these circuits will be taken into consideration. What about when V1 is less than 0? We're talking about this. So the output voltage will match this signal, but not the negative one. Only the signal will go like this, and then 0, then like that, then 0, then like this. So all of these are be considered, disregarding these. Now, what happened when V1 is less than 0? That means right away we can know that D2 is off. And we already know Vn is equal to Vp is equal to 0. Why? Because it's ideal op amp. And also D1 is equal to, is on. We can say is on. So in this case, op amp is acting as an inverting amplifier. In this case, V0 is equal to negative R2 divided by R1 V1. That's the ratio for the gain. We already have this one by using voltage divider. So let's assign, if we assign values, most likely V1 is equal to the absolute, V0 is equal to the absolute value for V1. I know you're going to ask how we consider this. Let's say we assign values for resistors. Let's say all the resistors are equal, 10K, 10K, 10K. So going back here, substitute R2 is negative 10 divided by R1 is 10. V1 is equal to negative V1. So most likely V0 is equal to negative V1 if we put everything together. So most likely for the second case, this is canceled and it will be equal to the positive. So this is when V1 is less than 0. This is when V1 is greater than 0. This is how a diode circuit with an op amp to rectify the input-output waveform. This is going to be page 3. Let's solve homework problems. Let me see if I can locate the some. Okay, let me share the screen with you guys so you can see what I'm talking about. Okay, now so most likely we are going to solve this problem. Since part B and C repeat, so we're gonna do only the first part, and you guys work it out. So we're gonna do problem 1.20 on page, what page, what page? So page 96. Page 96. So I'm going to read it, put the circuit, then come back and analyze it. So obtain relationship between V0 and V1 for the circuit of figure P120. If R1 and R2 are equal and P0 or VP is equal to 0. Hint, we need to apply two cases. So I'm going to put the diode in the output signal. So the diode is here. This is V0. Another diode here before diode number. And we have a resistor. And positive, negative, this is VP. This is V1, negative, positive. So this is R2. So we have everything we need. R1, V1. So most likely R1 is equal to R2. VP is equal to 0. And we need to take into consideration case 1, when V1 is greater than 0 and when V1 is less than 0. So let me unshare it so I can see. So, okay. So first we're going to take the first case, V1 is greater than 0. What happened when V1 is greater than 0? That means the current is flowing here. That's the current I1 flowing in this direction. This diode will be short-circuited, which is, let's call this is D1, D2. So D1 is on and D2 is off. So what happened when D1 is on and D2 is off? So most likely our V0 is here and this is short-circuited. So most likely we have the positive, negative Vn is here. So most likely Vn is equal to V0. Vn is equal to V0. We know that this is an ideal op-amp. So most likely Vn is equal to Vp is equal to 0. In this case, V0 is equal to 0. So the second case, this is part A. We're doing A. For V1 is less than 0, that means D1 is off and D2 is on. So the current on the second case is the current is going through. This is for the first case, number 1. For the second case, I1 is flowing in the opposite direction. So D1 is off, D2 is on. We can solve for for V0 is equal to negative R2 divided by R1 V1. So that means we don't have any values. V0 is equal to, since those are equal, negative V1. In this case, on, so V1 is equal to V0, the negative. And for part B and C, just repeat if R2 is equal to 2R1. So the value is a little bit different. I'll leave it to you. So let's get a paper. Page 5. Okay, now we're getting into three theory core materials, the semiconductors. Semiconductors are the most popular material. The materials that most popularly used in the semiconductor is the silicon, which is Si. So usually this silicon is element of group 4, because in the periodic table there's a group A and group B. So this is group 4 from the A side, A group 4. Usually why they name it group 4, because on the valence shell there's 4 electrons, which gives the ability to have another 4 to share. So if we are talking about Si is 14 electrons. So if I put the Si into into electric cloud, the first layer will only hold 2 electrons. The second one will hold only 8. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. And so 8 and 2 is 10. Left off is 4. 1, 2, 3, 4. And this is what called valence shell. Valence shell could hold up to 8 electrons. So the more stable, the more satisfied, or the better energy level on this. And so that's why the silicon, because this one have 4 and the other one have 4 available, 4 empty, so they will bond with each other. So semiconductors are most likely the popular in the industry for semiconductors materials. Each atoms, like if we put another, I'm not going to put in the inside. So each atom shares those 4 electrons with the close by silicon atom. Why? So they can form a covalent bond, and with this bonding, a lot of semiconductors properties will happen. We'll talk about it a little bit more. So most likely using silicon, the number of silicon that the atom per volume, the N as I, this is a constant. You need to remember that all the time. 5 times to the 10 to the power 22 atoms per centimeters cube. What is this number? This number is the number of silicon atom per unit volume. And this is atomic density. And also you need to remember the electron charge, which is Q. You know, if you took 210 or physics, you should be familiar with this number. Most likely 210, Coulomb. So usually during the thermal, why is the electron charge? Because during thermal aggregation, the bond between those atoms will break, because silicon will have a lattice assembly. And in this process, it will free one ion in between. So if we have a one silicon here, let's say all of them to connect it together. So usually to satisfy this one, to complete it, it needs to have 8. So usually it will get 4 from here and 4 from here, and 4 from here give to this one. So this one will give 4 and this one will give 4. They will share. So by the sharing, this one will have 8 electron to satisfy the valence shell, in this one 8 electron. So that does not give any options. So what happened during thermal aggregation, this bond will be broken and creating one of these electrons to change polarity. And this is what we call doping. We're going to talk about it more. So in thermal equilibrium, so what happened is just like everything is intact. So the number of electrons is equal to the number of holes. So usually this is the negatives and this is the positives. And they call this one also electrons per centimeters cube. And also this is called holes per centimeters cube. And this equal to Ni. N is the electron concentration or density. So, or this is most likely when there's an I next to it. So this is the intrinsic concentration. So for silicon, an I square multiplied with the absolute temperature is equal to just any constant multiplied with the temperature cube, e to the power Vg0 divided by Vt. This is the bond gap voltage, and usually is equal to 1.205 volts as a constant. So at the end, for silicon, the equation is Ni square T is equal to 1.5 1033 T3 E negative 14,028 divided by T, and this is going to be in centimeters negative 6. So at room temperature, this this temperature is equal to 300 degrees Kelvin. If you do that, so Ni is equal to constant 1.4 times 10 to the power 10 centimeters cube. So by doing all of these calculations. Page 6. Okay, doping. Doping is a term used for in semiconductors. But let me explain to you the whole concept about doping. So let's say we have a piece of silicon. So usually the silicon will satisfy each other by 4 to 4 bond. So let's say if we introduce one, either from the fifth or from the third group. So let's introduce one atom from the fifth group, which is phosphorus. Let's say this is Si, 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 and we produce the phosphorus here. So usually phosphorus, let me put it here. I'm not going to put the other, but the valence shell for phosphorus has 5 valence shell. 1, 2, 3, 4, 5. So silicon can occupy 4, leaving 1 freely. Let's say all this 4 and leaving 1. This is to play around. So usually with aggregating thermal energy at room temperature, probably 300 degrees Kelvin, this negative will be lost, will be floating around between the silicon. That's why this is what we call the electron doping. Electron, which is donor. Why? Because the phosphorus, 4 valence shells, electron is occupied with the silicon, but the fifth one is weakened with the link between the phosphorus and the nucleus of the phosphorus, so it will move freely. So most likely this is what adding electrons to the semiconductor. So usually this is a donor circuit. Let's say same piece of full of silicon, Si, Si. This is introducing group 5. And we're gonna now introduce group 3. So group 3, most likely boron. Boron on the valence shell has only three electrons. So most likely it will occupy and it will take one electron from this circuit, which makes it more positive, more holes. So there's like, let's say a positive ion is added to this circuit. So this is called acceptor circuit. So this is doping, could be in a donor section, or could be in an accepting or acceptor where the boron accepts or take one of the electrons, leaving one of the silicon with more holes, while the phosphorus, it will put more electron into these silicons, so it will be floating around, and this is most likely the donor section. So we can say in professional term, electric property of an element of group 4 can be altered dramatically by placing some of its atoms with atoms of elements from adjacent groups, because silicon is at group 4, so adjacent groups is either 3 or 5. So in this case, number of electrons, number of holes is equal to an I square, knowing that at room temperature, the temperature is 300 degrees Kelvin, so most likely an I squared is equal to 2 times 10 to the power 20 cm negative 6. So knowing that, for n-type silicon, so most likely N is equal to ND. This is the number of doping. So P is equal to Ni squared divided by Nd. And for P-type, silicon, number of holes is equal to Na. That means N is equal to Ni squared divided by Na. This is the concept of doping. Page 7. Okay, pay attention for this. I'm going to explain the drift and diffusion current. So a lot of students will be confused on how to define drift and diffusion current. I'm going to explain this with drawing what happened inside the semiconductor n-type, p-type. So first I'm gonna let's introduce, so usually the semiconductor will have two regions. This is all negative, and this is called N-type, and all positive are called P-type. The region that separates between both is called the P-N junction. So if we introduce an electric field in this direction, what happened? So we're gonna put line here, it's gonna be the same. So usually positive on this side and negative on this side. So it's many negatives. So what happened when you introduce electric field in this direction? So usually when the electric field is directed, see some of the negative here will jump into the P-type region, so negative here, and some of the positive will be jumping to this side here. So usually this, it will push the positive on this on the edge and the negative on this edge. So most likely it's not pushing. So most likely this space here is called space region. So this is, we can call, those are electrons in P region. And we can call these our holes in N region. So usually after it will be reaching equilibrium. So most likely the movement of the number of holes and the electrons in space region is called diffusion current. So when the negative jumps over, goes to the positive region, and the positive jumps over to go to the negative region, this space region, the movement of the positive and negative is the current, is the diffusion current. So we have reverse bias, we have forward bias, and we have drift current. So what happened in these three cases? So I'm going to put 3, 1, 2, 3. So usually this is the negative side. This is the N-type, and this is the P-type for all of them. And this is the P-N junction in the middle. So let's say if we put a voltage, so usually a positive here and a negative here. let's say this voltage is above its limit. What happened? So if we have negatives here, so I'm going to put, so when we put rigorous voltage or above the particular limit, the negative will repel the negative from here. It will push, so all of the negative will be pushed this way. So repel will happen. So most likely the negative will condense and push this way into the positive region, sorry. And what happened to the p-type, it will be also, because positive and positive, it will repel each other. It will push the positive to jump over. And we'll push the negative from this side. So usually what happened is we have a bunch of positive in the negative side and bunch of, but they're pushed due to the extra voltage that is applied to the terminal. So there's a repelling from the side and repelling from the side, because positive repel each other, negative repel each other. This is what we call forward bias. And for, let's say if we put same amount of voltage, let's say this positive side here and negative side here, and we put the same amount of voltage but negative on this side and positive on this side, and we put like a high voltage exceeding the limit. So what happened, the positive will attract the negative. It will be squishing all the negative to this side, and the negative will be attracting the positive on this side. And what happened here is there's all the negative will be on the side, and all the positive will be on the side. So we have like a few negatives and few positives. So usually some of these positive will go in, and some of these negative will go into the deep, into the p-type. And this is what happened when we have reversed bias. Last case, when we have a normal, when we have a negative here and a positive here, but not high voltage. It's just like a regular, whatever is required for this to happen. So most likely this will separate into 4 regions. We'll have a positive here attracted to the negative, and we have also positive here, negative here, attracted to the positive, negative here, but we have some negative jumping into here, and we have some positive also jumping into here, but not as much as the reverse bias. So in this case, this is called drift currents. So most likely the electron that moves around is called the drift current, similar to this case, but introducing the voltage. This is most likely the drift and diffusion current. If you didn't get this, you can read more in the book, but I think this is very explicit and straightforward. Okay, I think it's enough electronic circuits, semiconductors, and diodes for today. Homework, we're gonna call it chapter 1, part 1, due on, let's see, I will so due on 18, September 18, Friday by noon. And those numbers are, we already did 1.2, so 3, 5, 8, 11, 12, 14, 18, 25. So this is our week 2 lecture. And this homework is due by Friday on September 18. Submitted on Beachboard, Dropbox, folder EE 330, chapter 1, part 1, homework.